So, so current rockets, their drawbacks and our alternatives. So what are their drawbacks? Well, they're really inefficient. We can't really go that far with them. We can go to Mars with them maybe. We can't go to another star system with them. They're just not powerful enough or efficient enough. They can be further developed, like, not really. Tri-propellants, I guess, but like maybe double the efficiency. Not going to get us to Mars. Not going to get us to interstellar space. But they do have a future because if we want to get off the ground, we can't use these fancy rockets that need to go to interstellar space. They can't get off the ground really. Spin launch. How does it work? Well, you can see this arm thing here would essentially spin around and then just launch the payload outwards, just essentially throw it almost. And it would be better on the moon because the moon has no atmosphere and there's low gravity. And if you swing your arm around, don't do it because you're going to hit the person next to you. But if you can feel the air going around your arm. And so if we do it on the moon, then there's no air that's covering the arm and making it go slower, so it'll go faster. But we've got to get a spin launcher to the moon, which is hard. So it'd be cheaper than normal rockets because, well, we don't need a rocket, we just throw it. Sensible, really. So now this is the space elevator. So you can see how it works is we have the anchor at the bottom, cable going up, and then the counterweight at the top that would rotate with Earth, and the centrifugal force would keep the counterweight tight so it wouldn't just fall back down. Otherwise it would become a ground elevator. So then we have two climbers that could go up and down, and we could put someone in, put them to the top, and they could be in the top. And we could also put satellites in, and then a benefit of it is we put a satellite in, send it to the top, and let go of it. It's in orbit now. We don't have to use a rocket even. It's in orbit. Interstellar engines, I like this part. So the ion engine, how does it work? Well, if you'd imagine we get gas essentially, and then we'd ionize it to make it magnetic, and then we would use that magnet. We'd use a magnet to throw it forward, so it would then keep on going because of its velocity, and then we deionize it, so it's no longer magnetic. Because if we didn't deionize it, then all of this plume would go back into the magnet and stay in the magnet, and that'd be horrible. And it's very efficient, though. Although it's just a hamster pulling the spacecraft along, it's really efficient because it just can run for months and months and months. And it's already ready now. It's in space. It's in space. It first tested in 1966, I believe, and it's in space right now. The nuclear salt water engine. How would it work? It's essentially, if you imagine a nuclear reactor, and then imagine that running at 1,000 times what it's currently running at. That's what this would use, and then the water would get turned into plasma. That's what you see here that looks all nice, and then it would come out the back and as thrust. And it's not safe at all. It's essentially just a constant. It's like a nuclear bomb worth of energy constantly, just on and on, which is not good. Talking about fusion, how does it work? Well, imagine a jam donut, okay? And with a hole in it. And if you were to squeeze the jam donut, then there would be thrust. Then there'd be jam coming out, which would thrust you backwards because the jam's going this way, pushes you this way. Now imagine the jam is plasma. You wouldn't find this in the donut, and the end donut is now a tokamak fusion reactor. You wouldn't find this in Sainsbury's. So essentially, we'd have the hole in it, and this pressure would cause it to jet out. There you can see. It causes it to jet out, and it just has to come out really, and it doesn't really have a choice, and that would create thrust for us. I want it to explode if you drop it. Yeah, if it's running, yes, because it's a load of plasma. If it's not running, no, but the funding team will be furious. Antimatter torch engine. How does it work? It's quite simple. This engine, get antimatter, get matter, combine them together, that will just create thrust. And it's efficient. It is super duper efficient because we just need atoms of matter and antimatter to create enough thrust. And if you were, for example, a teaspoon of antimatter would be enough to blow up all of Manhattan. So the Alcubierre warp drive. That's weird. So, what this would essentially do is it would just take the place you want to go to you in 4D space, hop onto it, and put it back. Which is mind-bending and weird. And essentially, you wouldn't see it because light can't go through the fourth dimension. So it would just get close. It would get closer in the fourth dimension. You still wouldn't see it. It would hop onto it and then could leave. There is a video. We might play that at the end if we have time. So this is just a table. Nobody's interested in this. Carry on. So now, how do we live there? We've talked about self-sufficiency, habitation, and then health. Because if you've got there and we die, then it's not very good. Self-sufficiency. So, why is self-sufficiency necessary? Well, say we had an imaginary Mars base. You see, the thing is that to get to Mars, we can only get there once every few years because of the way transfer windows work. If Mars is on the other side of the sun, it's going to take a very long time to get there, many years, much more than 2. It's going to take a very long time to get there, and by that time Mars will have moved, so it's not very good for you, really. So, we need to make sure that if there's a problem, then we can last for 2 years and 6 months until we get help from Earth. So how would we stop actually? How would we do it really? So we'd essentially get water from the ice caps here. This is ice here, by the way, not snow. It is ice. But then we get water from it, and then we could use hydroponics, which is a way of growing plants and having fish. And the plants feed the fish feed the plants, and we can have fish and plant diets, which is fairly good for you. You could live on it. So what would a Mars base be like? Well, I have a little thing here. Think of a Mars base, okay? Think. You're probably thinking of this. I imagine most people are. You might be thinking of this. But I doubt many people were thinking of this. Then you can't really see the Mars base here, but it's this. Just we have to cover it in dirt. And that is because the glass here, for example, that there would be so much radiation coming in that after being there for 4 years, you just get annihilated by radiation, because that would double your entire lifetime dose in 4 years. So with this, the problem with this is if you're standing here, you can almost always see outside to the sun here. And if you can see the sun, then you're currently being irradiated.
Yes, sir.
Not good for you. So, what health issues have been identified? Well, if our appendix goes bang in space, then we have to have people running around us, and that's not good. And if our kidneys, for some reason, we don't know why, our kidneys just shrink in space. We still don't know why. So, could we extend our lifetime to allow for longer space travel? Yes, but one thing we need to remember is to extend our health span. Because if we just extend our lifespan, then we're going to spend another 100 years going in bed, and you can't really care for the hydroponics if you're going So we need to extend our health span so that you can care for the hydroponics for another 100 years. So how does gene editing help in space travel? Well, for a start, we could just gene edit away our appendix, just delete it, just go. And we could also fix our kidney problems, but that's a bit harder because we don't know what causes the kidney problems. And then how are humans likely to evolve? Well, for a start, in low gravity we'd get taller, and our muscles would also shrink. And so that would mean we'd have smaller stomachs because we don't really need much nutrients anymore. And then we could, when terraforming Mars, we might have like half an atmosphere worth of oxygen. And so the problem is that if we have half an atmosphere of oxygen, it's not very easy to breathe. So our lungs would likely grow downwards where our stomach used to be, and then connect to the bottom. Okay. Thank you. Any questions?
Alex Jonathan's got a question.
Okay, yeah, any questions? Oh, yes?
2 things. Number 1, you said you had a video of the warp drive one. I've heard of it, and I know the principles of it, and
Yeah,
I might want to see how it works.
Yeah,
Number 2, can we see that table again? Because I was really excited to see
Okay,
it.
we have enough time to think.